Welcome to another class of intelligent behavior analysis. Today we are going to learn about some aspects of kinematic analysis in complex human movements and some basic statistics that will help us characterize several parameters of the continuous complex motions of athletes and in particular, a famous individual who lost his proprioception. Ian Waterman will talk about that as well. Let me share the screen and begin the presentation. So again, this is intelligent behavior analysis and welcome everyone. Most of what I will talk about today is in chapter number 3 in our book for the class. I'll start out by talking about the notion of agency and self-determination, and we'll talk about that in autism and in other areas. The main objectives of the class today is to learn about agency, action ownership, and basic kinesthetic reafference variability. This refers to fluctuations in several parameters of our motions, our motion trajectories that we can record with various motion caption systems that we have already studied. We would like to learn about kinematics in complex human motions such as boxing, and about basic statistics and statistical properties of their kinematic parameters so that we can perform several analyses, build classifiers that allow us to automatically see different segments of complex human motions and so forth. So as we visited in last class, the notion of agency, agency refers to the ability to act independently and make our own decisions and have free choices. And we discussed different levels. The macro level of society, where we have different imposed structures in our agency curtailed by laws and regulations and rules. And then at a micro level, we talked about the notion of agency in our motor control, neuromotor control, and how that could fail and lead to having to rely on another person or another group of people because we can't even basically perform activities of daily life. So that level of agency is what we would like to focus on, and some of the ingredients that make up that ability, such as action ownership, and then beyond that, understanding the consequences of the actions that we intend to do and the actions that we are not intending to do because they're happening largely beneath our awareness. And one of the things that we're trying to do in this class is connect cognitive science with the body. So we're using the framework of embodied cognition to understand agency in a more comprehensive way, not just either as a brain related notion or a notion related to the function of the mind, or exclusively as a function of the body. The proposition here is that we should look at both in its full extent and understand how they connect, how they bridge the intent to move with the actual physical, mental intent with physical volition, physical action that is performed at will. We visited in the class the structures of the central nervous system and the peripheral nervous system. And roughly what we wanted to emphasize was the exquisite maps that exist already throughout the body and the face. And in this class, we will look at different ways to non-invasively quantify activity in all of these areas and connect aspects of social motor behavior necessary for social interactions at the face level and at the body level through the micro gestures that we can now track and systematically characterize the moment by moment fluctuations using our new techniques. We discussed Ian Waterman, the man who lost his proprioception, and I highly recommend to watch this video. It's fascinating, and it tells us a little bit about the neuroanatomy and the neurophysiology of the systems that are relevant to our class today. So please make sure to watch that video. We then would like to talk about internal models of action generation as they were conceived initially and as we have been modifying them over the years. In the internal models of action generation, there is a theoretical construct that studies motor commands as they are planned and executed by the brain in collaboration with the body. And so the idea is that the motor command exits the brain and goes into the peripheral system as an efferent information, meaning outwardly. And there is an efferent copy, also called corollary discharge, which has been extensively studied in fish and the fly system and other animal models. And this goes forward. It's called the forward model. And simultaneously, the motor systems carries the information, and through the sensory systems, there is a feedback that comes in the form of reafference or reentrant afferent information. One way to look at it non-invasively through kinesthetic parameters and the levels of noise that kinesthetic reafference convey. There is then supposed to be a sensory discrepancy between that forward model, the efference copy, and the current information that is in the system, returning as a reentrant information. And that sensory discrepancy produces an estimation, an error that serves for estimation of sensory feedback. And this would be a way to anticipate the sensory consequences of our motor actions. This model is quite oversimplified because the reafference actually is composed of exoafference and endoafference, meaning the information that comes from external space over which we don't have as much control as the information that comes internally from our own self-generated actions. And within that internal reafference or endoafference, there are several subdivisions owing to the structure of the system, mechanoreceptors, nociceptors, thermoreceptors, and the different channels that we saw in the movie by the BBC that Dr. Jonathan Cole spoke about, the different fibers. And in the case of Ian Waterman, the viral infection spared the pain and the thermal fibers, but affected the mechanoreceptors and the fibers that convey information about pressure, touch, and movement. And so that sensory feedback from movement is missing, and as such, he cannot compute that estimation of the action consequences through the endochannel. However, he can do so through the exochannels, and that exoafference is the visual information that he receives externally and integrates with his ongoing motions, modifying it accordingly. And this is a form of sensory substitution. So this model needs to be modified in many ways. One of them also refers to the different levels of intent that we have in our actions. Some actions are deliberate and intentional and follow specific goals. And some actions occur spontaneously beneath awareness and follow no instruction or goals. And we will see some of those examples today. Some of the motivations for the study of this internal model is the internal sensory motor delays. And these occur because of transduction and transmission delays and because of noise in every area of the sensory, noise and motor noise. So this is from a paper by Wolpert lab back in '99. That lab produced a first model of introducing the notion of noise in the motor system. It was an important milestone in the field of motor control. And this is a very nice picture that illustrates at many different levels what goes on when you try to catch a ball, for example, and you have to align the hand to the moving ball. And this is a dynamic process that involves motor control and the control of the sensory consequences that those motions produce. But at each level, at the level of sensory transduction and amplification of the signals that we get through the receptors, through the neuron receptors, we have cellular noise in the channels and in the synapses. We also have noise at the level of the systems and systems of networks of neurons when they transmit information to each other. Synaptic noise at the level of the synapses, and we also have noise at the level of the muscle and the motor neuron and the spinal cord, and transmitting information through the muscles and then back to the brain through the afferent channel. So many different levels of sensory and motor noise, and motor understood as a form of sensory feedback. In this case, it's important because through the kinesthetic reafference and through the reafference from motion and from pressure and from touch. So there's sensory transduction delays and sensory transmission delays in the travel time that it takes to go from point A to point B throughout the system. There is noise in every sensory motor transformation that occurs, for example, to align the hand to the ball shape and to bring it in front of the eye to measure that distance constantly. And there is also disparate time scales, for example, auditory systems, which are also involved in this, operate at the microsecond time scale, whereas other systems like the visual system operate in the millisecond time scale. And those disparate time scales have to be aligned into a common frame of reference to experience all of this information simultaneously. So how do we attain that? Well, the thought is that anticipating the sensory consequences of our ongoing actions and in particular anticipating the sensory consequences of our impending actions is what enables us to be a step ahead and compensate for those delays. And so the internal model of motor control, of internal model of action addresses these issues. So how do we, going back to agency and these basic ingredients, how do we connect it to mental decisions? So movement is a physical construct, and so we study all those physical acts. But how do we connect that to decisions, to mental decisions that are more of a cognitive mental space? So one of the things that we did in our lab was to define a taxonomy of neuromotor control, going from voluntary and deliberate motions guided by specific goals to all the way to autonomic motions that are not under voluntary control. And in between we have different layers such as reflexive, involuntary, spontaneous, and automatic. So automatic is motions that are quite well rehearsed and habitual. They were at some point learned, and now you don't have to think about them. As spontaneous, we see different types of gestures and embedded in our voluntary motions and actions are segments that we don't necessarily follow an instruction to perform them. They occur quite spontaneously. That's why we call them that. And they are distinguishable also for a type of spontaneous involuntary motions, which are at the very small micro gesture level. Involuntary are motions that we don't even realize they're happening, and reflexive motions are the reflexes, the basic reflexes that we have throughout the body. An autonomic example of that is the heartbeat, respiration, and related to it, and so forth. So how do we connect them to the decisions? Well, it turns out that in the decision-making world, there are different processes that can be mapped to several of these channels here, and they determine slow processes signaling deliberate thoughts and decisions, and fast processes signaling impulsive and reflexive decisions. So we have also a scale here that we can map decisions to actions and begin to think about this connection in our experiments. So for example, we study sports and athletes in motor control. And here's an example of boxing, which requires decision-making and requires motor control simultaneously. And so he will perform the jab, cross, hook, uppercut routine slowly, and you'll see what happens. And this is done at different speeds. So this is done at a fast or slow speed that is being called by the computer. And then what we do is we position sandbags in the forearm to offset the center of mass and to change the dynamics of the whole motion. And the movements become sluggish, and he eventually adapts to them. But what we're looking for is the differentiation between what he intends to do in punching an imaginary opponent here and what he is not intending to do. So we're looking at the consequence of both intentional acts and unintentional parts of the movement. And in the retraction of this motion, so the punch forward is the intended part of the action to punch the opponent in the face, the imaginary opponent in the face. And he's targeting that. But when he retracts to move the other hand forward with a different segment, so he does the jab forward, retracts, and then he does the cross forward, and then retracts the cross and does the hook forward and retracts, and then does the uppercut forward and retracts. And those retraction motions are not deliberate, they're not intended, they're unintended, spontaneous in nature, and they don't follow any instruction. And he did not know about them, even though he's a competitor and has been doing martial arts since he was 4 years old. So here's the other motion, right? And so it's slower because of he's adapting to those about 20 pounds of sand in each one. And so then we take them off, and then he adapts and he goes very fast. He surprises himself with how fast he goes. So he says it's so much faster, so much easier. And this is in contrast to the first, and this is within the same session, right? So this is when he's doing it at his own pace and or within a range of fast and slow that we are calling at random. So I'm going to compare the two again so that you appreciate how different the motions are. So here's after the adaptation. And these are sensors that record position. These are Pohimo sensors. They record position over time, and we'll be looking at the trajectories that the hand, this particular sensor at the hand, is producing. So these are produced by the hand, and this is decomposed step by step into the motions that he is producing. So the jab forward and then retracting and producing the cross, and then retracting and producing the hook and then the uppercut. So it all happens very fast. And so, but this is the whole motion: jab, cross, hook, uppercut. And here's what's happening, for example, in the left hand, which produces the jab and the hook. So the jab forward in this direction, and then backwards as the right hand is producing the cross, which is not shown here. And then it goes and produces the hook forward. It is very long and curved trajectory, and then backwards. And so the red portions backwards, he was not aware of, and these are the spontaneous or supplemental portions. They're unintended. So we discussed them in this paper that I uploaded into your box. And these are the speed profiles. Remember, we described how we build those speed profiles in the last class. And so for each one of the segments, and remember, this is continuously happening. So these are pauses that are between each one of the motions. So he starts out with the jab forward here, the jab forward, number one. And then that hand, the left hand, retracts. And simultaneously, the right hand is performing the cross as the left hand is retracting automatically. So this is a very spontaneous, uninstructed retraction. And I want to make sure that we understand the difference between automatic and spontaneous, because the automatic, it's hard to convert back to a deliberate motion, like when you're riding a bike, which is quite automatic, and you try to decompose it into deliberate segments. So that kind of obstructs the whole, impedes the whole motion. But this is not the case for the spontaneous retractions. You can ask the athlete to focus on those instead of the deliberate, and it will be quite easy for him to do that, to focus on the returning segment. But the default is that he wasn't even aware he was doing this. Then comes the hook. And as he is performing the hook forward here, this very long trajectory here, the right hand, so he's performing this with the left hand, the right hand is performing, is retracting from the cross, automatically retracting from the cross. And then he retracts from the hook as the right hand deploys the uppercut. And so there is this, now here's the whole left and right hand. So he deploys the jab, and as he then deploys the cross with the right hand, the left hand automatically retracts. As he retracts the left hand, the right hand, as he retracts from the cross automatically, the left hand deploys the hook. And as he deploys the hook, and the left hand then starts to retract, the right hand deploys the uppercut and then retracts. So that's the whole motion in slow motion and then in fast motion. And what I would like you to take from this is that so between fast and between slow and fast, there are fundamental differences in the trajectories that are unintended. So you will see these that they change shape and they become extremely curved when the for example, this is number 4 here, going from retracting from the uppercut. You see that this is less curved than this one. So the trajectories shape it's not that they're just varying, like here, there's a variability in the curve that is quantifiable, is that they actually change altogether the geometry, okay? And in the speed profile, what you see is a conservation of the shape of the speed, but it's shrinkage, so by about half. So this is a little over 4 seconds, it's almost 2 seconds. So, but similar structure in the speed profile. And remember, these are derived from the positional trajectories. So now we go from position to speed. And so again, go back to make it easier to look at. In the left hand, we just focus on the jab and the hook. And this is the jab and the hook forward for slow and fast. So no matter what the speed is, you have variability in the trajectory, but you don't have a change in the basic shape and length of the trajectory. And so this is the speed profiles. Remember, these are performed at random. They're called at random, interspersed with fast. So these are the slow, interspersed with the fast curves, and they are different. Okay, so this is again from different speeds, randomly performed, and then we go and we gather those that are slow and those that are fast for each one of the hands. And what we then noticed is that, for example, here in the uppercut, when we get all of the slow trajectories, they are fundamentally different in a different class of geometry. These are quasi-straight, these are very curved. When the motion is motion is not intended. So the unintended motions convey this enormous amount of information about the dynamics of the body. These are the intended segments, which conserve their geometry despite the changes in speed. So the intended segments are invariant to dynamic changes. They are geometric invariant. The unintended segments are very sensitive to all these nuances of the dynamics, the context, and so in the exercise of placing mass in the forearm to offset the center of mass, these trajectories remain invariant. They remain along the same type of geometric class. But not the retracting trajectories that are not instructed or that are spontaneously happening beneath the player's awareness. Okay, so now we take those peaks in the trajectory in the speed profile, and we put them all. We measure them trial by trial, and we place them along a scale from low, medium to high, and then we bin them sorted into bins that in meters per second tell us how fast each one of these trajectories, and we think of them as they come at random. So they have, some of these movements are slow, some of them are very fast, some of them are medium, and we place them in the corresponding bin. Right? And so some of them overlap because we have many measurements like here. So it's difficult, they're similar, but we know that they're not the same. So it's difficult to see. And what we do is then we stack them up and tally them, and we can then see how to build a frequency histogram. So then they are within the same bin interval, and we're stacking them. In the next class, what we will see is ways to quantify these with the command histcount and histogram. So this is now counting, and we tally their frequency per bin, and that's how we build a frequency histogram. So now we take all of those peaks from the speed profiles that we constructed from the trajectories, and we can build a histogram. And what you can see is that it has a heavy tail, it's not symmetric. And in the case of these control participants, what we can do is take the log, and when we take the log of the parameter value, we see that then we recover the distribution is symmetric, and it can be modeled by the log normal distribution. So this is the histogram of the speed data. And what it's telling us is that when you look from trial to trial, it's very likely that the next trial will be in this region of the histogram, rather than here, which would be rare occurrences because only a few occur there. But nonetheless, they do occur. So they have a heavy tail distribution. So they're skewed. And so this comes from our data. And then what I would like to introduce you to is to a different type of distribution, which is the exponential, where you have most of these higher frequency clump into this area. And this is a special kind of distribution. We call it memoryless, and it's a random distribution. And so it's difficult to predict next events based on past events. And what we will look today is at how to, because we will see that they show up in our research, how to estimate this curve with maximum likelihood. So the exponential distribution is a statistical distribution that models the times between events. For example, how long will it be before another motion will occur in the range of 5 meters per second speed, like when we have our athlete moving? How long will it be before you get another phone call? How long will it be before you get another text message, and so forth? So this is the type of process. It's a random process, and we're looking at the amount of time or at the temporal structure of event after event. So here the y-axis is a scale so that the total area under the curve equals 1, and that's how we measure. We'll see how measure probabilities. So what is the probability of events with a speed between 0 and 2 meters per second? So we solve for the area under the curve spanning between 0 and 2 meters per second. So that's our probability. And this is the equation that describes the exponential distribution. The lambda parameter is the rate parameter, and is proportional to how quickly things happen from moment to moment. And we will be studying today how to derive this parameter lambda for a given string of numbers x. So like a vector array of x values. So in this case, for example, they come in meters per second because they indicate the peak velocity. And to be more precise, is the peak speed. The velocity is a vector, and we are talking about a scalar. So a scalar quantity, which is the speed, which we measure with a norm. And we saw that with the Euclidean norm, we measure the moment-to-moment change in position, which is the velocity vector. So the peak speed is modeled here as after an exponential process. So the exponential distribution, so lambda is proportional to how quickly things happen and reflects the amount of time between events. For example, the rate parameter here equals 1, and this is the curve that we obtain for a particular set of x values. And so there's a model reaching a given speed value every second in this case. So every second we register an event. So here's the blue curve for lambda equals 1, and we contrast it with the red curve when lambda equals 2. So lambda now models reaching a given speed value twice every second. So in this case, we're representing seconds. And so now we contrast the blue curve for lambda equals 1 and the red curve for lambda equals 2 with the black curve here for lambda equal 0.5. So models reaching a given speed value once every 2 seconds. Okay, so we can examine the different values of the rate parameter for different data sets. And then then we go into maximum likelihood estimation. Given a set of measurements, find an optimal value of lambda. So what is the optimal value of lambda for your set of measurements? So for example, for your data, when you're typing certain characters, when is the next character going to be typed? And so it modeled that type of event. So for example, a time series of events reflecting the timing between some occurrence. A text message, a heartbeat, the speed peak of a continuously random sample motion, the keystrokes on a keyboard, the touches on a cell phone screen, etc. So let's say that your measurements come from a sensor and it's telling you these numbers moment by moment, and they correspond to x sub 1, x sub 2, x sub 3, and so on, x sub n. And we assume that we have a lambda value representing this event. So in this case, for example, we are measuring the number of times, the number of speeds per second, centimeters, and the speed, the centimeters per second, the peak, the amplitude of that peak, moment by moment. So in each moment in time, we register this parameter and we build a random process that way. Okay, so then we assume that we have a lambda value and we wish to know the likelihood of lambda given those values, given the value. So the likelihood of lambda given the value x sub 1 would be the model after lambda e to the minus lambda x sub 1, and that gives us a number because we are assuming a lambda value. And the likelihood of lambda given x sub 2, so that would be lambda e to the minus lambda x sub 2 and so forth, right? And if we were to plot it, we would, and the lambda was correct, we would be falling right on the curve of the exponential distribution. So this would be my x1 value and the y corresponding y1 value for the particular rate parameter that we have. This would be the x2 values, and this would be the corresponding y2 value for that particular lambda. But the point is, how do we determine this lambda given this string of numbers? And so the likelihood of lambda given both x1 and x2 would be then the product of the likelihoods, and substituting here by the formula, then we have the product of lambda e to the minus lambda x sub 1 times lambda e to the minus lambda x sub 2. We apply these rules of multiplication and come up with this expression. So now that we have this expression and we do that for all the x sub n, or from x sub 1 to x sub n, and we get this product, we end up with this expression here, applying these rules, right? So lambda is being multiplied n times, so it's lambda to the end, and then we have the exponential term, and applying the rules of the exponential, we can take the lambda out and sum over all of the parameters. So this is how, so the question is now, what is the likelihood of lambda given all the values in the time series that you have? So this would be all your keystrokes, for example, when you're typing, on all your times of your text messages, all the times of your phone calls, etc. How do we determine the optimal lambda in general? So we want to know the lambda. So to determine the optimal lambda in general, so we take the likelihood of lambda given all of these values in your time series, and this is the formula that we computed, replacing the lambda e to the minus lambda x by. So we take the derivative of this formula here, and we solve for lambda. when the derivative is 0. Okay, so those are the two steps that we're going to take. And the reason for that is, okay, we plot here for each value of lambda that we are estimating, for different values of lambda, right? We take the likelihood, right? So we take the value of that formula, plugging in our time series value. And so if for a given lambda, so that the likelihood is low, so that say that that lambda is not too good, then we increase the value of lambda, and the likelihood changes, and so on and so on. So we can measure the slope of this curve that we form, and in some point it's going to be maximal. So you're going to have the maximum likelihood value given the lambda value that you choose. And that's how we're going to determine it. So at the maximum likelihood, the slope of the derivative is 0. And so that's why we solve for lambda and when the derivative is 0. So we take the derivative of the likelihood function with respect to lambda. And this gives us now when the fact that when the exponential is in that term, like here, it's easier to take the derivative of the log of the function. And the derivative of a function and the derivative of the log of the function equals 0 at the same point. So they are interchangeable, and we can take then the derivative of the log instead of the original formula that we came up with. So we're going to do that. And so we take the derivative of the likelihood function for all our time series, and we follow the rules of the log. So this is the product, so it decomposes into the sum of the two. And here, the log of E is then just comes to the expression of our time series, and N comes here by the rules of the logarithm. And I invite you to revise all these rules. And then the derivative of the log of lambda is 1 over lambda. And so now we have an expression which is quite simpler, and we equate that to 0. Because then this is the second step to take the derivative, to set the derivative to 0 and solve for lambda. So we just do the algebraic steps, and our lambda, maximum likelihood estimation of lambda is this. So given your time series, this is the maximum likelihood estimate, or the MLE, for lambda. And so we can now model this exponential process given your data, right? So we found the optimal lambda for all those values. And I invite you to do this for the Gaussian distribution. This can be done for any of those well-defined distributions. So now we have our lambda, and we can then make a distinction between the likelihood and the probability, because usually we interchangeably use these terms, so they're not the same. So the likelihood of the distribution given the data, okay, is we have the likelihood, the y-axis values for fixed data points with distributions that can be moved. And so given the point, you can estimate the value and change the point. You can estimate the value given the data, right? So this is given the data, you can estimate the value. And so you can estimate what the distribution is given the data. On the other hand, what is the probability of the data given your distribution? So now what you have is the distribution, and you can then go and see the probability of the data as the area under the curve that you have for your distribution, okay? So if the data lies here, then that's your probability, is the area under the curve. And remember, this is such that the sum of all adds up to 1. So you can do that for the normal distribution, for the gamma distribution, for the exponential distribution, and you can see how the grouping is different for each one of these distributions, and we can study, we'll see in the class how to generate these graphs and how to study different distribution and different maximum likelihood estimations for a sample data set how to estimate the maximum, using maximum likelihood, the probability distribution that best fits your data, okay? So in the case of the normal distribution, say that you assume a theoretical mean over here, but your actual data is over here. So your empirical mean really is off. So you can compute, given your normal distribution formula, you can plug in those values, and you can and set the theoretical mean and compute this value and compute the error that you incur so compute the likelihood, essentially, or compute the probability. And in this case, given the data, so there is low probability or low likelihood, now you know how to compute both, right, of observing these values for the theoretical distribution imposed a priority. And that theoretical distribution imposed a priority has a particular mean that you have assumed, and it doesn't align with the density of your data. So if you shift now the normal distribution by shifting the theoretical mean to match the empirical data, then your likelihood will be higher, and your probability, the area under the curve, will be higher as well. So higher probability or higher likelihood of observing these results, these values, for the theoretical distribution that you imposed a priori. Likewise, you can continue to shift, but then you fall out of the area of the optimal area for your mean. But this is just an example, just to see how you can then again incur in low probability or low likelihood of observing these values for a theoretical distribution imposed a priori. I want to bring this up because a lot of times this is how science is being performed. So all the statistics that you see are imposing a theoretical distribution a priori, not only a theoretical distribution like the normal distribution, but also imposing a mean and testing against that hypothesis. Right? So this is an incomplete form in several ways. And one of them is that most likely the data that you're trying to model does not even fit that, the empirical data does not even fit that theoretical distribution. Okay, so again, the likelihood of observing the data can be estimated using your probability of the data given the mean and the variance, the parameters of your distribution here. So here you would have these parameters set a priori and plug in the data and compute the area under the curve, versus the likelihood of the mean and the variance of your distribution given the data. This is what we just did with the exponential distribution, and I invite you to do that with the Gaussian or the normal distribution, okay? And so you have, again, empirical data here, grouped with the density over here. You can compute the density for each one of the assumed means, and then estimate the likelihood given your formula. Just plug in your values here, okay, for a given mean and a given variance. Plug in your values and you get a value for the likelihood. And as you travel and shift your mean and your variance, then you will find the optimal likelihood. And you know, by shifting the location of the distribution center, you will see when your likelihood is maximum, okay? So this location maximizes the likelihood of observing the empirical measurements. The normal distribution mean coincides with the empirical mean here as the data accumulates more densely in that area. So I invite you to derive the likelihood, the maximum likelihood for the normal distribution. Okay? We can do that first by setting the mean fixed, and then setting given the data, and then setting the variance. And so we can go over that in class. Okay? And that's the maximum likelihood estimation for the mean, and can do the same for the standard deviation. Okay? So now we go back to our profiles here from a speed to frequency histogram, and we can then replot the frequency histogram for the deliberate segment punching to the imaginary opponent, which is the target. The face of the opponent is the target of this. And also the supplemental activity or spontaneous activity, which is does not have a target per se. And this is the the log normal distribution by taking the log of the parameter and fitting the log normal distribution. Does a good job at modeling this type of data. Okay. So when we finished characterizing our the basic statistics of our data here, we decided to run a leave one out decoding algorithm, which you break the training, your data set into a training set and into a testing set. And so given the speed peaks, we ask which type of movement does it belong to. So in the blind, given a trial that has a particular speed peak, or if you do it with the position data, you can ask, for example, the bending profile, the curvature, given the curvature of the trial, picked at random, what most likely, what is the likelihood or the probability that this particular value belongs in a particular movement, okay? So first we characterize each one of the movements into classes of probability distributions, and then we cycle through the data that we're training this set with, and then we will test data that we didn't cycle through, that we leave out. And each time we leave out one trial, that's why this is called leave one out decoding algorithm. So how informative is the trial by trial variability in our data set when you cycle through all the sets? We took an expert and we took 9 novices from college age, and we took 1 autistic adolescent. So first we'll do the neurotypical controls. We divide the set of all trials into the training set and the testing set. And at every iteration, we show the training set to the algorithm, but leave out the one trial that we want to test. Then we measure the prediction error. And so, as a reminder, here we have the speed profiles. We're using the peak here of each one of the profile of the segments, and we're segmenting the data for both the right hand and the left hand, and we're adding all of that together and presenting it to the decoder. And what you see here is a confusion matrix, and it's divided into 8 different cases. And so each one of the cases represents, each one of the bins represents the jab deliberate and the jab spontaneous, the cross deliberate and the cross spontaneous, the hook deliberate and the hook spontaneous, and the uppercut deliberate and the uppercut spontaneous. And this is the group prediction, and it's quite good because along the diagonal is quite high, so it's tending to 1, and off the diagonal, which are the confusion terms, are low. So for example, the jab is primarily, is over 80% of the time classified as the jab, and only confused with a hook, and is confused about 20% of the time. And you can see it here. So this is the jab and the hook, right? The cross is never confused. It's at probability 1. It's never confused. The hook is confused with the jab. We saw that already. And the uppercut is somewhat confused with the cross and the hook, but below 2%, so below 20%, below 0.2. So this is in probability 0 to 1, but it also, you can express in percentage 0 to 100. And overall, so the spontaneous segments, retractions, are perfectly decoded. So there's no confusion there. And what we see that most importantly is that here we don't have any confusion between the deliberate segments and the spontaneous segments. So they're all at 0 confusion. So we took also the worst individual, so that that could perform the worst performer, and we see that now that the probabilities decrease along the diagonal, and in the spontaneous segments there is some confusion, for example, between the jab and the hook, and the jab and the uppercut, for example. But there's still no confusion between the deliberate segments here and the spontaneous segments. So this is the real values along the way to read this graph is the real values and the predicted values. So these are predicted by the decoder. We then came across a serendipitous discovery in that we were testing different athletes, and the captain of the lacrosse Rutgers team at that time brought her brother, who sat here. This is her brother, and he is autistic, and he was playing video games there the whole time that she was performing all of these. And we decided to see if he wanted to perform this experiment of the jab, hook, cross, uppercut, and other martial art routines. You're going to see here other martial art routines. We asked him if he wanted. He said yes, but he had never done martial arts, and he had not paid attention either, or we thought that he hadn't. But what happened was that immediately he mirrored the expert and did all of these in sequence, whereas it took everybody about 4 sessions to piece up all the sequences and do it in a fluid one shot. And so we were very impressed with him. But then we study the motions, and this is where the segments, all the markers are, and we study all the motion of the full body, and we're able to study all the trajectories in detail. And what we discovered was that his spontaneous motions were not as distinguishing as well. So remember, in the controls, the typical developing, we could distinguish for example, here in the uppercut, we could distinguish, in the retraction, we could distinguish the slow and the fast segments because they change curvature. But in the autistic, we couldn't do that. They were identical. So this was also characterized by the exponential distribution. So now I have shown you about the exponential distribution. And so the deliberate segments in the autistic case were exponentially distributed. So the events in the past were not informative of events in the future. You just have access to the information, the here and now. Whereas the spontaneous segments were similar to those of the controls. We plot them on a parameter space, fitted the gamma distribution, and we're able to fit an exponential decay curve to them. And we saw that the autistic individual, the deliberate segment, was quite exponential. So it was at 1, the value of 1 in the gamma distribution. So initially we had modeled this as a log normal distribution, but the log normal distribution does not include the exponential distribution. And so we decided then to apply maximum likelihood estimation, and it turns out that these are well fit by the gamma distribution, which is a continuous family that includes both the exponential distribution and these heavy tail skew distributions, and also symmetric distributions. We then rerun the decoding algorithm. And remember, for the case of the controls, we had the group prediction was pretty good. It didn't confuse deliberate and spontaneous unintended movements. And even for the worst performer, the most naive individual who didn't know how to perform these routines. But in autism, this was not the case. So in the case of the autistic individual, the movements that were deliberate were confused with those that are spontaneous. And one of the propositions here was that understanding the unintended consequences, the sensory consequences that come from unintended actions, helps us understand what we intended to do from what we didn't intend to do. And so it it sheds light to the concept of action ownership, which is fundamental to the concept of agency. And so this was a case where we studied both the curvature of the positional trajectory and the maximum speed of the trajectories. And in both cases, the system was confusing deliberate with spontaneous sensory consequences, deliberate, intended with unintended sensory consequences. So we were able to quantify this in autism. Okay, so for the next class, we are going to characterize intent through different types of processes, inevitable, spontaneous, and deliberate. And inevitable is a very interesting class of process that we will talk about in the next class. And with that, we conclude the lecture today, and we invite you to go and look at the materials in the box and in the Canvas website.